Hi everyone, my name is Saif and this is the fourth lecture and the final lecture which covers the modeling and simulation of DC motors. In this lecture, series connected DC motors presented. Now we are following the same procedure we've been presenting in the last three lectures. So the DC machine, the series connected DC motor, is modeled using three different approaches. The first one is to use a block diagram, which requires to find the transfer function of the machine. The second one is to use the built-in blocks in Simulink Simscape library. The third one and final one is to use the built-in DC machine block already built in Simulink to test and validate the first two models presented. To find the transfer function of the system, we are following the same four steps. First, we have to find the equations which describe the machine, identify the inputs and output variables, and then take Laplace transform of those equations. We're assuming that the system is linear time invariant system. Now the transfer function of the system is a ratio of the output to the input variables. Now since the machine is connected in series, the armature circuit and the field circuit are connected in series to the same voltage source, which is Vt, as shown in figure 1 and presented in equation 1. Since both circuits are connected in series, the field current and the armature current are equal. Now equation 3, which represents the armature circuit in terms of their self-resistance and self-inductance, and the voltage induced in the armature circuit, which is commonly referred to as back or counter electromotive force, which is a multiplication of the rotating speed and the mutual inductance between the armature and field circuits multiplied by the field current. In equation 4, the field circuit is represented where the self-resistance and inductance of the field circuit are multiplied with the field current. The electromagnetic torque presented in equation number 5 in terms of the mutual inductance and the field and armature currents. Also the relationship between the electrical and mechanical quantities of the machine presented by the load torque, the inertia of the rotor, of course, in addition to any mass connected to that rotor, in addition to the damping coefficient associated with the mechanical rotational system of the machine. So the inputs are the total voltage, or it's simply the armature and field voltages, which is rewritten in terms of the armature current plus the load torque. The output of the machine would be the rotating speed as shown in equation 9a and 9b. Now, in order to simulate the machine, we're using the parameters presented in table 1. These parameters are taken from reference number 3. And as we mentioned earlier, we are using three different approaches. The first one is to present the machine using block diagrams. And we are using the components found in Simscape library in Simulink to build the model of the machine. And the final approach is to use the DC machine block to validate and double check the models we already presented and built. Now references cited earlier in this lecture are presented here, and we've already started MATLAB. Now we can start Simulink by either writing Simulink in the command window or just switch the Simulink block from here. Okay, so we're using a new model and we are calling Simulink library from library browser, and in order to build the first model we're going to use libraries from Sinks. So we have to have the scope block, we have to have from sources, we have to have a constant, and from continuous we have to have the transfer function block, in addition to the from math operation, we're going to use the gain and, well, divide and sum. Alright, so I guess those we have to use. So let's go and build that model. Okay. So let's use the brackets. So the torque. Alright, so what do we have? We have the transfer function, which represents the electrical side of the machine. We have the other transfer function, which represents the mechanical side, let's say, of the machine. And the final output, which is the speed. Let's just write speed, I guess. Speed. we have the armature current, the armature voltage, the field voltage, and the load torque, plus the mutual inductance between the armature and the field winding. I've already saved. So I've already saved the machine parameters in an M file, and simply just run that M file in order to have those parameters shown in the workspace. Okay, so let's go back. Alright, so before running the model, let's double check everything, I guess. Yeah, so we have to change this sign to negative, right? And let's run the model, probably for a bit longer time, let's say 60 seconds, and see the output. So the rotating speed is basically building up to around 220, I guess, around 204, 5. Okay, so this is the first step, this is the first model. Let's go and build the second one. So we'll need the Simulink library again, but this time we would like to use Simscape library. So we'll go to the fundamental library, electrical elements, and let's just make some room for the other component. So we have to have then an inductance, of course electrical reference, resistance as well, and let's just push them a little bit down. Alright, we would like to have a controlled voltage source, which is this one, and from sensors we like to have, well, both, I guess, current sensor and voltage sensor. Okay, now this is from electrical library, from mechanical library. We have to have, well, from sensors we have to have ideal rotational sensor, which is this one. From sources we have to have ideal torque source. Okay. From elements we have to have an inertia, mechanical rotational reference, plus rotational damper. And from utility we have to have both converters, so power system to Simulink and Simulink to power system, server configuration, electrical circuit, and for the mechanical circuit we need two server configuration. Okay, so let's start building. Let's borrow those components. So this is the current, the armature, or the field current. Probably wouldn't need that. Okay, I guess this is the electrical side of the machine. Now let's try to build the mechanical side. We have the inertia. This is output, rotating speed. I'd like to have the signal feed back to electrical circuit. Okay, so let's rearrange a little bit the circuit, and this is the same load torque. Okay, brilliant. Let's just put this one a little bit further, and so we have the armature circuit, the field circuit, and let's go and set those parameters similar to what we already presented. So this is the armature circuit, so self, inductance, and resistance. So resistance and inductance for the armature circuit, resistance and inductance of the field circuit. Let's check if we would get the same speed. All right, and let's put both of them, compare both signals from so this is a signal coming from the first model, the signal coming from the second model. Let's check if they are identical. So I guess they are. Yeah, they are. All right, let's double check by presenting built-in DC machine. Which is this one. Let's make a room for this machine. To use this machine, we have to have the Power Graphics User Interface block. Probably it's easier to use search to find it, I guess. Let's put it here. Let's push it a little bit downward. Make a room for that block. Let's go and use sources. So we can use, let's use 2 blocks. So one for the field and one for the armature winding. Okay, so the signal of the field voltage is taking from the same block, been using for the 2 earlier models, and for the torque as well. Simply connect this one. So this is trying to tied up a little bit these blocks. Okay, that seems right. So we need the mixer, because we have more than one signal coming out from the machine. Basically we have 4 signals. We can check the signals coming out from the DC machine by going to help. Meanwhile, let's set those values. So this is RA. Right, so this is the help. So basically we have 4 output. So the rotating speed, the armature current, field current, and electrical or electromagnetic torque. The first signal is for the speed, and hence we basically need to change this to 4 outputs, and we just need to check if the speed is similar to the speed produced by the previous two models. So back to parameters. So RF, which is the resistance, self-resistance of the field winding. Mutual inductance. Can just set those to 0, I guess. Okay, so let's run the model again and see if we will get the same results. Yeah, so if we put the output of the three models together and check if we will get the same speed, the same signal from the three models. Yeah, I guess we do. So with doing so, we concluded the modeling and simulation of series connected DC machine. And if we have been, thank you for watching.